All right, so today we're going to be taking a deep dive into the world of multimodal learning in healthcare.
Okay.
And specifically, we're going to be looking at this paper called Weakly-Supervised Multimodal Learning on MIMIC-CXR.
That's a mouthful.
It is a mouthful, but I promise you it's cooler than it sounds.
All right, I'm intrigued.
So basically the idea here is we're trying to teach computers to diagnose illnesses.
Okay.
But instead of just using like an X-ray or just using patient records, we're using all this data at once.
Oh, wow.
And that's what multimodal learning is all about.
I see.
But the problem is getting all that data labeled by experts is really, really hard.
Yeah, it's a big challenge.
It's expensive. It's time-consuming.
Absolutely.
And so that's why this research is so interesting, because they created this model called the MMVM VAE.
MMVM VAE.
And it's actually able to get really good results even with limited labeled data.
That's awesome.
And to help us unpack all this, we've got our expert here with us today.
Happy to be here.
So one of the things that jumped out at me in this paper was how a lot this MMVM VAE is doing compared to other methods.
Right.
They were using chest x-rays for this research.
Okay.
And it seems like it's really outperforming other approaches in terms of predicting diagnoses.
Yeah, they were really focusing on combining frontal and lateral chest x-rays.
Oh, interesting.
And that's not something that's been done super effectively before.
And it's not even just combining them. It's like this model is somehow making the lateral x-ray, which is kind of the less informative view, more useful.
Yeah.
How are they doing that?
So that's where this concept of soft sharing comes in.
Soft sharing. Okay.
Yeah. So think of it like this.
Okay.
Imagine you're trying to figure out what an object is.
Okay.
And your friend describes it to you.
Mm-hmm.
That gives you some information.
Right.
But then you also get to see a picture of it.
Okay.
And so each piece of information adds something unique. And when you put them together, you have a much better understanding.
So it's like you're cross-referencing what you see in one image with the other one.
Yeah, it's like the model's becoming a detective, piecing together clues.
That's really cool.
From different sources to get that complete picture.
And that seems like it would be a big deal, especially when you consider how hard it is to get labeled data in healthcare.
Absolutely. It's a game changer.
So does this model actually deliver on that promise?
Okay.
Like, does it actually work well with limited data?
That's a great question. And that's what they wanted to find out.
Okay.
And the results were really promising.
Okay.
So they compared the MMVM to these other models that need a lot of labeled data. And not only did the MMVM perform better.
Wow.
It did it using only 10% of the labeled data.
Okay, 10%?
10%.
That's amazing.
And pretty incredible. I'm looking at figure 1 from the paper right now, and you can really see the difference.
Like visually, it's very stark how much better it's doing.
Yeah, it really drives home the point.
Even with just a fraction of the data.
Absolutely.
Okay, so there's another figure that I wanted to ask about, figure 5.
Yeah.
This one shows how the model can actually generate a frontal X-ray image.
Oh, yeah.
If you only give it a lateral one.
You got it.
Is that right?
That's right.
Yeah.
It's showing off its generative capabilities.
So it's almost like it can fill in the blanks.
Yeah, it can.
Which could be super helpful if you're missing one of the views for some reason.
Exactly. And that has a ton of implications for clinical practice.
Oh, wow.
You know, imagine a patient can't have both views taken.
Right.
Or one image is corrupted or unavailable.
Okay, so now my mind is like really racing with all the possibilities here.
It's exciting stuff.
But before we get too carried away, we have to ask about the limitations.
Of course.
Like, what are the caveats here?
So one of the big ones is that it's mostly focused on chest x-ray. So it needs to be tested on other types of medical data.
Right.
Like electronic health records or different types of imaging.
So we need to see if this approach can be generalized to other areas of healthcare.
Yeah.
Okay, well, I am officially hooked. I want to know how this thing actually works.
All right, let's get into it.
Like, what's going on under the hood?
Let's do it.
So in the next part, we're going to unpack the architecture of this MMVM model.
Sounds good.
And really explore what makes this whole soft sharing mechanism tick.
Looking forward to it.
All right, this is going to be good. Okay, so we've talked about how this MMVM VAE is doing some pretty impressive things.
Yeah.
Especially with that whole soft sharing idea. But now I'm really curious. How does it actually work?
So it's all about how the model is designed.
Okay.
It's architecture.
Right.
So imagine it like a recipe
Okay.
with specific ingredients
Yeah.
that work together to create a delicious dish.
Okay, I like that analogy. So what are the main ingredients of this MMVM recipe?
So the core components are called encoders and decoders.
Encoders and decoders. Okay.
And you might remember those from when we talked about VAEs in general.
Yeah, those were the things that kind of compressed the data and then tried to rebuild it.
Exactly.
Okay.
So in the MMVM, you have separate encoders for each type of data.
All right.
So in this case, with the chest x-rays, there's one for the frontal view and another for the lateral view.
Got it.
And they take the image data and extract the essential features, creating this condensed version.
So each encoder is like a specialist.
Exactly.
Focusing on one specific type of X-ray.
Got it. They're like summarizing a long book into a few key points.
Okay, that makes sense.
Yeah.
What about the decoders?
So the decoders do the opposite.
Okay.
They take those condensed summaries and they try to rebuild the original X-ray images.
Oh.
And the better they are at reconstructing the original images. The more we know that the model has actually learned meaningful relationships within the data.
So it's like a test to see if it actually understood what it was looking at.
Exactly.
If it can rebuild it accurately, it means it got the important stuff.
It got it.
Okay.
And so here's where the soft sharing magic happens.
Okay.
Instead of keeping the information from each X-ray view totally separate, the model uses something called a data-dependent prior.
A data-dependent prior to encourage connections between them.
Okay, hold on. Data-dependent prior, that sounds...
It's a mouthful.
Pretty technical.
Yeah.
Can you break that down a little bit?
Sure. So imagine you have a friend who's really good at guessing games.
Okay.
They start with some basic assumptions, but they're constantly updating those assumptions based on new clues that you give them.
All right.
So that's kind of what a data-dependent prior does.
Okay.
It helps the model adjust its understanding of the data as it learns. So it's not just blindly following a set of rules.
Right. It's learning and adapting.
It's learning.
Okay.
As it goes.
That's pretty cool.
Yeah.
How did that tie into the soft sharing, though?
So this prior, these assumptions, they encourage the model to find links between what it sees in the frontal X-ray and the lateral X-ray.
Got it.
It's like the model is saying, hey, these two views are related.
Okay.
Let's see how they connect.
So it's getting a more holistic picture of what's going on.
Yeah.
It's not just two separate images.
It's one patient.
It's one patient.
With two different perspectives.
Okay, I see.
And that's why that lateral view, which is usually less informative, becomes more useful.
Okay.
Because by connecting it to the frontal view, it can extract more meaning from it.
It's almost like our own brains.
Exactly.
We take in information from different senses.
Yeah.
And we combine it to make sense of the world.
That's a great point. Multimodal learning is kind of inspired by...
how our brains process information.
Okay, so we've got the encoders, we've got the decoders, we've got this soft sharing, guided by the data-dependent prior.
Yep.
Anything else in this architecture that we should know about?
Yes. One more key ingredient.
Okay.
Is the mixture of experts approach.
Mixture of experts. Okay.
Yeah, we've talked about that before.
We have, but I need a refresher.
Sure.
What does that mean in this context?
So think of it like having a team of specialists, each with their own area of expertise.
Right.
Instead of one generalist trying to handle everything, you have these experts working together, focusing on different parts of the data.
So instead of one giant model trying to understand everything, we've got these smaller, more specialized parts that can focus on the details.
That's the idea.
Okay.
And that's super helpful when you're dealing with complex, multimodal data. It lets the model be more efficient and effective at capturing those nuances.
So each expert brings a different piece of the puzzle.
Exactly.
And together, they create a more complete picture.
That's it.
Okay. I think I'm starting to see why this MMVM model is so good at what it does.
It's a powerful combination of techniques.
Yeah.
And they've really put a lot of thought into how to make it work.
But I am curious.
Yeah.
Why does this work better than other approaches?
Okay.
You know, the paper mentions some alternatives like averaging. Or something called product of experts.
Yeah.
Why is soft sharing so superior?
So it all comes down to how you combine the information from different modalities.
Yeah.
So averaging, for example, tends to treat all the modalities equally. Which can lead to a loss of unique information.
So you're kind of blending all the colors together.
Exactly.
And you end up with this muddy brown.
You lose the distinct characteristics of each input.
You lose the vibrancy.
Exactly. With the MMVM soft sharing, each modality is allowed to contribute in a more meaningful way. It preserves those unique details while still finding connections.
So it's finding that sweet spot
Exactly.
between shared knowledge
Yeah.
and individual insights.
It really highlights the ingenuity of the design.
Yeah.
It's not just about throwing more data at the problem.
Right.
It's about understanding how to integrate the data effectively.
This is so much cooler
I know, right?
than I initially thought it would be.
It's really fascinating.
The way this model is designed, the way it learns, it's really pushing the boundaries of what's possible.
Absolutely.
Okay, so now that we've explored the technical side, I kind of want to shift gears a little bit and talk about the bigger picture.
Well,
like, what does this research mean for the future of healthcare?
That's the big question. I feel like we've really gone deep into this MMVM VAE model.
I know, right?
It's fascinating.
There's so much complexity there.
Yeah.
But now I kind of want to talk about like the bigger picture.
Right.
Like, what does this all mean for the future of healthcare?
That's the big question.
Yeah.
And I think the potential is huge.
Okay.
One area I'm really excited about is diagnostics.
Okay, we talked about how it could generate those missing X-ray views, but like zooming out even further, how could this change the way we diagnose illnesses in general?
So imagine a world where AI can analyze not just an X-ray, but a patient's entire medical history.
Wow.
All at once.
Okay.
So their lab tests, their genetic information, even lifestyle data.
Okay.
You could integrate all of that to get a much more complete and personalized picture of their health.
It's like having this superpowered detective working alongside the doctor, finding these patterns and connections that a human might miss.
Exactly. And this could be really impactful for conditions that are hard to diagnose. You know, we could potentially catch things much earlier.
Right.
Leading to better treatments and better outcomes.
That's amazing.
Yeah.
And it's not even just about diagnosing illnesses.
Right.
I'm also thinking about treatment planning.
Yeah.
Could this kind of AI help create those more personalized treatment plans?
Absolutely. Instead of this one-size-fits-all approach,
right,
you can imagine treatments tailored to each patient's unique needs and characteristics.
It's like going from mass-produced medicine to like bespoke healthcare.
I love that.
Customized for each individual.
It's a great way to put it.
And it doesn't even stop there.
No.
Like, what about drug discovery?
Yeah, you could use AI to analyze tons of data.
Right.
To identify new drugs.
Okay.
And even personalize drug regimens.
Wow.
Based on someone's genetic makeup.
Okay, my mind is officially blown.
Yeah, it's pretty amazing.
But I also want to be realistic here.
Sure.
Like, every new technology has its challenges. What are some things we need to be thinking about as we move forward with this kind of AI in healthcare?
So I think one of the biggest challenges is making sure it's accessible to everyone.
Okay, yeah.
We want to make sure that these advances don't just benefit a select few, that they're available to all patients.
Right, because we've seen that happen with other technologies where benefits aren't evenly distributed.
Yeah.
And we definitely don't want to see that in healthcare.
Absolutely.
We need to be really mindful of those social and economic factors that can influence access and make sure that these AI tools are designed in a way that promotes equity and fairness.
Very well said.
I'm really excited about the potential for AI to improve healthcare.
Yeah.
But I also want to acknowledge the role of human doctors.
Right.
Are they going to become obsolete?
I don't think so.
Okay.
I think human doctors will always be essential.
Okay.
You know, AI can be a powerful tool, but it can't replace the human touch.
Yeah.
Empathy.
Yeah.
The ability to connect with a patient.
So it's not about replacing doctors.
It's about augmenting their capability.
Giving them these new tools to make better decisions.
Exactly.
Yeah.
The ideal future is one where AI and human intelligence work together.
I like that.
Each playing to their strengths. AI can handle the data analysis and pattern recognition.
Okay.
And doctors can focus on the patient experience and the emotional support.
That's a vision of the future
that
I can definitely get behind.
Me too.